Hello everyone, today we are going over section 3-11, which is normal forces and tension forces. And just so I come back up here, 3-11, normal and tension forces. So I want to start off just going through some of these quiz questions. These are a little less involved, and then we'll go over some example questions. And yeah, let's get started. So whenever you are in contact with a surface, let's say this is you right here, and you look at that 1 foot, that 1 foot is touching the ground there. Whenever you're in contact with a surface, you are exerting a force on it. That force in this case is downward because you are standing atop this pavement and you are exerting a force downward. Now at the same time, the surface is exerting a force back upon you. And if we were to draw the free body diagram of just you, so this is you, this little box, you're just this box now, because like imagine you're a mime and you're inside a box, that's you now. So if we were to draw a free body diagram regarding the forces acting upon you in this very instant, we would see that your weight, the gravitational acceleration times your mass, is the downward force. And remember, equal and opposite forces. So you're exerting a force, let's say this is force X, on the pavement. That pavement is exerting the same force in the opposite direction against you. That's force X in the opposite direction. And since we're drawing the free body diagram of you, specifically, we see that force appear, and we see that appear on your free body diagram in the upward direction. And this was X, and it's basically this force there that I just drew over, and this is our normal force. This is this is our weight force here. Sorry, that is a miscommunication, misspeak. So this is F sub W, and this upward force, this is known as the normal force, and it's the normal force because it's normal to the surface that is that you are in contact with. And if you can tell by, let's draw it out without all the chaos, we see that the direction of force, imagine this little dot is you. The direction of the force is perpendicular. It's perpendicular to the surface you are in contact with. So going over 3-11 quiz question 1, the normal force is blank to the surface of contact between objects. As we saw through this drawing out of the free body diagram, the answer is B. It is perpendicular. It is at a 90-degree angle. Moving straight along here, 3-11-2 asks, a book is at rest on a table. Then a person puts their hand on the book and presses down. The upward normal force on the book from the table is blank, the downward gravitational force on the book. So let's draw out a free body diagram. We have this table. We got that table. I don't know how it's standing, but it's standing. And we have a book on it. And let's imagine that book is right at the edge. And then someone has their hand straight on it there. What are the forces acting on that book? Well, we have a downward force for our weight force, so F sub W. We have the force of the table on the book, and that's our normal force. It's perpendicular, as you recall. It is perpendicular to the surface of the object that it's in contact with, so this is the normal force. And we also have a downward force, another second downward force. Let me make it a little nicer there. A second downward force, that is the force of your hand pushing down, so force of hand. That's an H. So we know that this book is at rest. The problem states that it's at rest, which means that these forces must cancel out. So if these two forces here, this one and this one, are in the negative direction, we know that F sub N has to be equal to F sub W plus F sub H. And we know that both of these are negative forces. These are in the negative direction. So from there, we can then say that F sub N minus F sub H equals F sub W. So this then means that if we were to analyze this, if we were to plug in numbers, this could be 8, this could be 5, and this could be 3, that compared to the downward gravitational force, right, the normal force is greater than the gravitational force, because the weight force plus the force of your hand on it are equal to the normal force, meaning that neither of these two components separately are greater than the normal force, and only when combined they equal the normal force. So the normal force is equal to the sum of the forces acting downward on the object, and that is why C is our answer. Less than answer A would suggest that if the normal force was less than the gravitational force, that the book would fall through the table. Same with if it was equal to, because we still have this second force acting downward. If F sub n, so let's just scribble that out. If F sub n, if the normal force was equal to the gravitational force, then when we are considering us pressing down on that book, we basically break the table. Like, there goes our table. I mean, I spent like $100 on that table. I don't want that book breaking through that table. But anyways, that's what equal to means. That would also, these both mean that the book breaks through the table. Because these are equal and opposite forces, and these two forces are counteracted by the normal force, as stated in the question, that is why C is the answer. Let's consider this next question with this pulley system. So, we should consider the 3 50-kilogram boxes. They're all at rest. And we have to figure out if the tension on this rope, rope 2, is greater than the tension on rope 1. So let's draw a free body diagram for each of the 3 blocks and see what's happening here. So here's block 1. So this is 1, this is 2, this is 3. And we see that there's a gravitational acceleration downwards, so our weight force, and then the tension on the rope. So we'll just label that T. Now for block 2, and we know that this is at rest, so let's just round the gravitational acceleration to 10. So we could say that this is 500 newtons, and since this block is at rest, the tension is 500 newtons as well. Now for block 2 and block 3, so block 2 and block 3, does the situation change because these are connected? Does block 2 affect the upward force of block 3 at all? And let's just draw the downward forces first and see if it makes sense that either of these two blocks affects the tension of the string, of the rope. So we know that the downward force is the force of weight, and we know that the force of weight, the gravitational force, weight, is equal to mass times the gravitational acceleration. So as we said, we round that off to 50 times 10, so this is 500 newtons. And the same goes here because it's another 50-kilogram box, that it is 500 newtons. And we know that this is at rest, so we know that the upward force must also be 500 newtons. Now, because these blocks are connected, does that mean that the tension on this rope is 1,000 newtons? Is it 1,000 newtons because both of these blocks are pulling down at 500 newtons? Well, no. If this was, let's say the tension on this rope was 1,000 newtons, that would mean that the upward force on each of these blocks is 1,000 newtons, which would then mean that the block is accelerating upward, which, given the problem statement, does not make sense because we had started with the sentiment that the block is at rest. So it doesn't make sense that the tension is additive to each of these blocks. It makes more sense that the tension on the rope is equal to the downward force acting on a specific block. And you can imagine this as two separate pulleys, or as two separate systems, because these two blocks are not directly interacting with each other in any specific way. You can imagine that this rope up here ends at the ceiling, and this rope up here ends at the ceiling. And the math works out essentially the same regardless, because this block is at rest. Now, if there was some acceleration going on, we would then have to consider other information, but because these blocks are at rest, we can then say that these two forces cancel out to a net force of 0, which means that the tension force acting on rope 2 is equal to the tension force on rope 1. And that is the answer. One last thing I wanted to say about this question is that the reason we were able to make so many assumptions about this question, this is a very simplified version of a question that you could get. It's because these masses are equal and the sentence states that the blocks are, or the problem question states that the blocks are at rest, which means we were allowed to make a bunch of assumptions about the system itself, and in order to make the conclusion that the tension was between these two ropes was equal. However, if we have a different mass for one of them, let's say one of the blocks was 70 kilograms, we would have to consider the forces acting on each block. And if you want to learn more about how to actually calculate that for blocks of different masses, I have a video linked in the description below by Khan Academy that goes over this in depth. There are multiple examples. I found them helpful, and I believe you will as well, so hopefully you find them helpful. And yeah, now we're going to move on. The final question that we have here is 3-11b, which states, a box is being pulled to the right at an increasing speed by a rope that is angled upward. The surface is frictionless. So that means that there is no force in the opposite direction. So let's just erase that. There's no force in that direction. And the surface is frictionless. Consider the following statements. 1, the normal force on the box is equal to mg. And 2, the acceleration of the box is equal to the force vector t divided by the mass of the object. So let's write out the relevant equations going on here. So we have force equals mass times acceleration. So we can reorganize this as force divided by mass is equal to acceleration. So that's what this statement is referring to. And then we have the second statement. The normal force of the box is equal to mg. So this one's referring to the fact that when you have a surface on the ground, the normal force is the force of the ground acting back upon the block. So let's first, again, it's always good to draw out the force body diagram for this block. So we know we have this downward force, our weight force, mg, so F sub W, and this is M. And it looks like when we draw out this free body diagram, we have this T force, and it's right now is such, so that's T. Okay, and then we also have the normal force acting upward, so F sub N. So looking at this, we see that there are two vertical upward components, one vertical downward component, and one horizontal component. So let's break this down into the just solely vertical and horizontal components. So let's redraw this. We see that F sub N, and we have this smaller force, T. We have a horizontal component of T, and we have F sub W. And we know, based on how the diagram looks, so this is M, we know that based on how the diagram looks, that the box isn't being lifted off the ground when it is being pulled at this angle, which then must mean that the vertical components of the system cancel out, which means that, let's draw it right here, F sub N, that's in a double, well, that works too. F sub W is equal to F sub N plus T, tension. So that must mean, statement 1, the normal force on the box is equal to mg. Well, let's extrapolate this further. F sub W, the weight force, is m times g, mass times the gravitational acceleration. And if the normal force plus tension is equal to mg, that means that the normal force is not equal to mg, but it is instead equal to mg minus t. So that's what the normal force is equal to. So statement 1 is false. Let's consider the second statement here. The acceleration of the box is equal to the force vector t divided by mass. So it's kind of going off of this statement here. However, we have to consider that the tension is at an angle. So when this tension is at an angle, we have to remember our SOHCAHTOA rules. So this force vector here is t, but this the horizontal component is, because we have the angle is touching both of these components, it is t cos theta, and we don't know the angle. It's not stated in the problem, but that's not really relevant. This is a theoretical question, a conceptual question more than anything. So the horizontal component of this, which in turn relates to the acceleration of this, because we know that the vertical component cancels out, it doesn't contribute to the acceleration on the block. We know that the horizontal component is equal to t cos theta. So that means that when we plug this in, t cos theta over m is equal to a, which is not what the second statement is saying. This is saying that just the force vector itself, t, divided by the mass is equal to acceleration. Well, that's not the case. So therefore, looking at the potential answers of which one's true, D is the correct answer, meaning that neither of them are true, and we showed it through our work here and here. And that is the last question we have for Unit 3-11. Thank you so much for watching. Hopefully you found this helpful, and have a great day.